Distributive property. When it's a monomial against a polynomial, it's pretty straightforward. A lot of this is review because first class of the new year. A little memory refresher is in order. So we have 3a multiplied by 4 and then multiplied by the a. Right? So when you multiply monomials, you keep the base, add the exponents, but you also multiply the coefficients first. So what I like to do, and you might remember this, is I go through and I give every variable an exponent. Right? So this would be 3a to the first, and also a coefficient if there isn't one already there. All right, so this a over here should have a coefficient of 1, but also an exponent of 1. All right, now that 4, I leave this sort of as optional because that 4 technically has an a to the 0th power attached to it. So you could say 4a to the 0th. But you could also just kind of leave it alone, knowing that you're really just multiplying the 3 by the 4 and sort of disregarding the variables there. It's up to you. All right? I already wrote it, so I'm just going to kind of leave it. All right, so if I multiply the 3a, a to the first, by a 4a to the 0th, 3 times 4 is 12. For the a's, I keep the base, add the exponents. So a to the 1 plus 0. So a to the, I'll write the 1 plus 0 this one time. But you would really just write an a, right? Because it's kind of overkill to write the 1 plus 0, right? So that would be the result of that first computation. The second computation would be taking the 3a to the first and multiplying it by the positive 1a to the first. All right, so 3 times 1 is 3, positive 3. All right, a to the first times a to the first, keep the base, add the exponents, a to the 1 plus 1. There's a lot of fluff here that you wouldn't need to write. I'm just doing it for review purposes. This would really just simplify down to 12a plus 3a squared. All right. So again, there's a lot of extra things there that you wouldn't do if you're doing this on your own. But in terms of the theory, it's kind of important to at least consider that that's what's really happening behind the scenes. All right. So number 2 involves a fractional coefficient, but it's really the same skill. So I'll run through this one without all the bells and whistles. All right. So we're taking that 1/3 and we're multiplying it by each term inside. All right. So the 1/3 is going to get multiplied by each of the 12z and the 18z squared. But since it doesn't have a variable attached to it, yeah, I could put the z to the 0th power adjacent to it, but it's not going to serve a purpose because all I really need to do is think, okay, I'm going to take this 1/3 and multiply it by just the 12. I'm going to take the 1/3 and multiply it by just the 18 because it doesn't have a variable associated with it. All right? So this would become 4z plus 6z squared. So you get it much quicker. I mean, like I said, I could have put the 1/3 z to the 0th, throw in a z to the first, and keep the base, add the exponents, and all that stuff, and that would have been fine. It's just, it's a lot of extra steps to not really have much of a payoff.
What did they mean in parentheses when they say write as the sum of monomials?
Oh, it's just each one of these terms is a monomial. So your final answer should have a sum, or, well, a difference would work too, but it should have a sum because if it's still separated by parentheses, it's not fully distributed.
Got it, thank you.
No problem. So then the next couple of problems, we have, it's multi-stepped. All right, we have a monomial being distributed against a polynomial, but then you'd have to simplify a little bit beyond that based on combining like terms. All right, so we'll just focus on one part at a time here. So we look at this guy and we'd say, all right, I'm going to take that 6x and distribute it to each term within this set of parentheses. All right. This x has an understood exponent of 1. So does this one. And again, as sort of a shortcut, we're learning if it doesn't have a variable attached to it, it's just going to take on whatever the variable is of the multiplier, right? So when I multiply 6x by 2x, I get 12. Keep the base, add the exponents, x to the second power. But then when I multiply the 6x by the 3, when I multiply it by the 3, or the negative 3 in this case, the exponent's just going to come along for the ride. Or, the variable and the exponent are going to come along for the ride. I'm just multiplying the coefficients. I'm going to get a negative 18 x to the first, but I'll just write that as negative 18x. But then I'm going to do the same thing with the negative 5. I'm going to run that through using the distributive property. So any variable and associated exponent is going to come along for the ride. I'm just multiplying coefficient by coefficient in each case. So negative 5 times 2 will give me a negative 10, so negative 10x squared. Negative 5 times 9, so negative 45. Bring the x along for the ride. Negative 5 times negative 3, positive 15. The added step here is that we have to combine some like terms, right? Now, that's covered in this little statement here. To simplify each of the following expressions, when they say simplify, they mean down to its simplest form, right? So it's kind of implied, but it's also just kind of what the term means, right? So if it can be simplified further, it must be, right? So I go across the line here, and I say, all right, well, I got a term here that has a power of 2. Do I have any other terms with a power of 2? I do. I'm going to combine those. All right, so I got a 12 minus 10. That's going to give me a 2. So 2x squared. I look at my second term. I see it has an x to the first power. I look for another term that has an x to the first power. I have another one there. So negative 18 minus 45 is negative 63, I believe. Negative 63x. And then we just bring the 15 along for the ride. All right, there's no counterpart associated with that. All right. The next one, number 4, is very similar to the point where, I mean, it'd be kind of overkill to do it. So I'll let you try that one on your own. But I wanted to get to binomial against binomial and binomial against other types of polynomials. So number 5, and then, well, really, actually, any of 5, 6, or 7, but definitely number 8. All right. So I'll do number 5. It's fine. When you're multiplying a binomial by another binomial, the only thing you have to remember, and this is the same for any kind of polynomial by polynomial situation, you're multiplying each part of the first polynomial by each part of the second polynomial. Right? So I would look at this and say, I have an x. That x needs to get multiplied by the x and the negative 12 in the second binomial. Right? So this x has to go to each part of the second binomial through multiplication. So I say, all right, well, what is x times x? That's x squared. Keep the base at the exponents. X times negative 12 is negative 12x. All right. Then I do the same thing with the negative 7. Going to run that through the other binomial using multiplication. The negative 7 gets multiplied by the x, giving us a negative 7x. The negative 7 gets multiplied by a negative 12, which gives us 84, I think. Little multiplication tables. We're going to work on a geometric way of looking at this tomorrow, but for now it's just a skill. All right, so combine our like terms. We only have one pair of like terms, negative 12x and negative 7x. Both have powers of 1 associated with them, so negative 19x. Everything else comes along for the ride. and that would be our simplified form. All right. So again, once we get rid of the parentheses through multiplication, it really is just a matter of saying, all right, let's simplify by combining like terms. Once we do that, it's all over. All right, mission accomplished. And you could check on a calculator, but I think I mentioned this before the break. It can be fairly tedious. I mean, be reasonable about this. Doing problem after problem after problem of this variety can be tedious in and of itself, but taking your answer, typing it in, taking the question, typing it in just to see that the graphs match up, you know, like you do that once or twice, but if you have to do it for every problem, it's going to double the length of time it would take to complete an assignment. So what you do is you save that for the situations where you're a little nervous about your answer. Like, I'm not 100% sure about this one, so let me have a look. And what I mean by that is you just type in, let me just get a fresh Desmos here. You type in the original expression, and Desmos lets you type it in as just a standalone expression, not an equation. It's kind of weird. It shouldn't actually do that, but it does, so we'll take advantage of it. All right, so if this were an equation, if this were a y equals, this is what it would look like. So then I would graph what we just came up with in the simplified form. And just verify that they give the same graph. If they do, then we know that what we have is equivalent to what the original question was asking us to simplify. The only thing is we wouldn't know if we went far enough, because you could easily take this second to last step here, pop that into Desmos. It'll still give you the same graph, but it wouldn't be the complete final answer or correct final answer. So there'd be a little bit more to it than that. But this idea of taking every part of one polynomial and multiplying it by every part of another polynomial, that's consistent no matter how many terms there are to the polynomial. Grab number 6 now. That's a couple of binomials being multiplied. All right, so in each of the previous cases that we were working on, we had monomial multiplied by polynomial. Now we want to do polynomial times another polynomial. All right, the only thing that you have to remember, you know, aside from little things like making sure that you distribute negatives and such, but really the big idea here is that each part of the first polynomial has to get multiplied by each part of the second polynomial. Right? So when I'm looking at number 6, I would start off with that negative 10w, this one right here, and I'd say, all right, I have to take that 10w and multiply it by each part of the second binomial, which means it has to get multiplied by this 10w and by this 1. Now again, there's an understood power of 1 associated with the w. So 10 times 10 is 100. W times w, well, keep the base out of the exponents, w squared. 10w times 1, positive 10w. You could write the power of 1 if you want, doesn't matter. All right, so that takes care of our first distribution. Our second distribution is going to come into play when we look at this negative 1. This negative 1 also has to get distributed to each part of the second binomial. So I'd say, all right, well, what's negative 1 times 10w? Negative 10w. Whenever you multiply by negative 1, you're just taking the opposite of whatever the number is that you're multiplying to. So if I take a 5 and multiply by negative 1, the result is negative 5. If I take an x multiplied by negative 1, the result is negative x. If I take a 10w, multiply it by negative 1, the result is negative 10w. You're just slapping on a negative. If it was already negative, you're taking away the negative. All right, so little mental shortcuts, because now I can look at this and say, well, I'm not figuring it out. I'm just going to take the opposite of the sign. All right. Now, one good thing about these are called, well, you'll see it in a minute, but these are called difference of perfect squares. One good thing about a situation like this, where you see that the binomials have the same structure, same numbers, but the sign in the middle is different, is that the outer and inner terms, or the two, in this case, the two middle terms, would actually cancel out with one another. Because we have two opposites, 10w and a negative 10w. 10 minus 10 is 0. So this goes to 0, and we just have a 100w squared minus 1. This will come in handy in the next unit when we talk about factoring, because we're going to have to go from this back to that. And being able to recognize these relationships is going to be really helpful. But at this point, if you know, oh, I see another one of those binomial situations where the only difference is the sign in the middle, this is going to be pretty easy because a lot of stuff is going to cancel out. That's what you kind of want to be on the lookout for now. All right. Let's do number 7. We'll do 7 and 8. All right. So number 7, same general idea in the sense that they're two binomials, but the relationship is somewhat different. You know, it's not made up of the same exact ingredients. You know, they both have positive signs, so it's not like they're alternating signs. But we could still use the same approach where we take each part of the first polynomial and multiply it by each part of the second polynomial. So again, this is an assumed power of 1. 2 times 2 is 4. Keep the base, add the exponents, q to the third. 2q to the first times 1. Well, anything times 1 is itself, so that's going to be plus 2q to the first. Well, we could just write 2q. Then we're going to run through with the positive 1, meaning we're going to take that 1 and multiply it by each term in the second polynomial. Anytime you multiply by a 1, you're not making any change. 1 times a number is that number. So 1 times 2q squared is 2q squared. 1 times 1 is 1. So this is very, very close to the correct final answer. I mean, it's like 3 weeks ago now that I mentioned this for the first time, but we want to have our answer in descending order. All right, descending order means highest powers come first, then the next lower, then the next lower, then the next lower. So you see here, we have power of 3, power of 1, power of 2. We need to swap this term with this term, bringing the signs along for the ride. So our final answer would be 4q cubed plus 2q squared plus 2q plus 1. All right. So see, every one of these problems has a little quirk to it, but they're all the same general structure in that, what are we doing? What's the main skill? We're taking each part of the first polynomial and multiplying it by each part of the second polynomial. What we do after that is specific to the types of polynomials that we're working with. All right, sometimes easier, sometimes more challenging. In fact, looking at number 8, you'll see that this one looks like it's probably the hardest one, but it actually cleans up the nicest out of all of them. All right, but it's the same general structure. I'm going to take the first part of my first polynomial, but instead of multiplying it by only 2 terms, I now have to multiply it by 3 terms. W times w squared, or again, assumed power of 1. Keep the base, add the exponents, w to the third. W times a negative w, well, both of them have assumed powers of 1. A positive times a negative is a negative. W to the second, keep the base, add the exponents. W to the first times a 1, well, anything times 1 is itself, so plus w to the first. Again, you could omit the power of 1 if you want. But I learned in the last problem that could kind of come back to bite me, because if I have to have my answer in descending order, it's nice to know that I have everything in the right order. You know, so I'm going to take that 1 and multiply it by each term of the second polynomial. In this case, it's a trinomial. So plus w squared minus w to the first plus a 1. I ran through that pretty quickly because we're only multiplying by 1. When you multiply by 1, you're not making any changes. Whatever these values are, they're just going to get replicated in our solution. But something really nice happens here. If you look carefully, you see that the like terms, with the exception of the w cubed and the 1, the remaining like terms are all exact opposites of one another. So I have a negative w squared here and a positive w squared. All right? I have a positive w to the first, and I have a negative w to the first. Anytime you add opposites together, the result is always equal to 0. So all of this stuff cancels out to equal 0. So the only thing you're left with is the w cubed plus 1. All right, because everything else is going to cancel out. I mean, if you really want to show the work, then you move some things around. You know, have the negative w squared and the w squared adjacent to one another before canceling them. But I think that's a wasted step. I mean, since you know you're allowed to do that, move some things around as long as you bring the signs with them, then what's the point? You know, like if you know they're going to cancel, just cancel them. All right, but you're left with a w cubed plus 1 and maybe a lot of concern that maybe you did something wrong. There's always the technological approach, right? You can always go back to the calculator to have a look and see if what you just came up with is equivalent to what you started with. I mean, it can be tedious from time to time, and you could use x's instead of w's. So, I mean, I'll try it with the w. W. W squared minus w. The difference is if you do it with an x, it'll create a graph. If you do it with the w, it'll ask you for a slider, but that's fine too. We're just looking for equivalence. So I took the original expression. I have a slider. Depending on where I put my slider, it'll give me a particular value. All right. So then I would do the same thing, just with the simplified expression, just typing it in, creating a slider, except the slider would be the same slider. With the idea being that if I get the same decimal value in each case, depending on where I put my slider, then I know I have equivalence. Now, if I did this with x's, it would give me 2 graphs, and if the graphs matched up, then they would be equivalent. But this one, you know, it's consistent with the variables used in the problem, and it's kind of nice. You know, it's very visual. It's like, okay, let me put my slider here, same value. Let me put my slider here, same value. Slider here, same value. Doesn't matter where you put your slider, same value. All right. So either way is perfectly fine. Yeah, like I said, if you put all this in with x's, you could do that too. But maybe you look at this and say, well, that's way too much effort to check this one problem. Yeah, I kind of pick and choose my battles. When I simplify something, you know, that's similar enough to other problems that I simplified, like you're doing an assignment that's got 20 problems on it, you don't have to check every one of them, especially since like 3 or 4 of them are similar, you're pretty confident. But then when you get one that's crazy and you feel like you did a lot of work, you're like, you want to have a quick look, you know. So I leave it up to you. It's not a requirement, but it's definitely more and more useful as the math gets more and more complicated.